We talked about some power functions, right? We looked at, well, if we look at this group of power functions, let's say just like f of x equals x to the 1 through x to the 6th, what can you tell me about what they look like? So, okay, so they do get, the higher the power of x, the more squared off. What kind of symmetry, group them into two groups with different symmetries? What could you say? Name a function that has, out of that group, that has line symmetry or reflective symmetry. X squared. What's another one? What's another one? Etc. So the common, obviously, and that's why we call them even functions, right? Because they're even exponents. Okay, and then all the others that have odd exponents would have that odd. And what kind of symmetry is that? Odd symmetry? Rotational about the origin. Good. Okay. Good. So what about domains and ranges? What's the domain going to be for that function? Doesn't matter which one I'm pointing at. Yeah, it's going to be all the reals, isn't it? Right. And why would that be the case? Let's talk about that. We can look at the graphs. That's fine. We can look at the graphs. Like if we were to look, for example, let's just take. Well, I might as well just graph it. Let's just take like x to the 4th. Okay. From the graph, you can kind of see that this is going to keep on going up forever and out to the side forever. It might appear, you might ask the question, well, does it ever start to go so vertically that it hits an asymptote? Because there are functions that do that. Like if I were to, for example, graph the function like if I were to graph this function, y equals 1 over x, this, if an ant were to walk to the left along this blue function, he would climb increasingly steeply, and he would never ever get to the point x equals 0. That is asymptotic. But this one is not. Okay? And so, how do you know from the graph? Well, maybe you don't exactly. You could just zoom out and keep zooming out, and you can see that it goes to the side forever. But let's have a little more advanced conversation about this, about the domain. Let's not just purely just look at the graph like we did at the start of the year. Why is it if I take those two functions and we want to find the domain, that this one, the blue one, has an asymptote at x equals 0? It can never get there. The ant runs up against this wall, but the red one doesn't. If the ant climbs the red function, either walking backwards to the left or forwards to the right, he will always continue to move, horizontally. There is no x value that he wouldn't get to. He'd get to a trillion at some point. He'd get to a Google. He'd have to go really, really high to get there. But there's no limit to how high you can go, right? So why is that? Let's look at this in a little more advanced way. So let's compare these two functions. The red one was y equals x to the 4th, and the blue one was y equals 1 over x. What do you think? And you told me that the domain of this one was all reals. But the domain of this one is not. The domain of this one is x cannot equal 0. Right? Any other value is okay. He can walk on this part of the function over here, or on this part of the function over here, but they're completely separated by this vertical asymptote. Okay? Suggestions? Just by looking at the function. What were the two things we said we couldn't do when we talk about real numbers? Okay, so we can't square root. We can't take an even root of a negative number. That's true. And we'll talk a lot more about that in the future. But for now, that one's not as important. It is one of the things we said, though. What's the other thing? Can't divide by zero. Yeah. Does that seem to be an issue here, maybe? Look at this function over here. Is there any value of x we could ever pick that would force us to divide by zero? There's not, is there? How about over here?
Yes.
Yeah, there is. Zero itself, right? And what I like to tell my calculus students is you just want to look for the red flags, right? You want to look for the places in a function where a variable could cause you to divide by zero. And look, there's a variable in the denominator right there, right? So that's where we got to be careful, because x, the default would be, we'll assume x can be anything until we find out there's something it can't be, right? So is there a value here that would cause the bottom to be zero? An obvious one. Yeah, x can't be zero, right? See what I'm saying? And so, yeah, the domain we would expect, because there is no red flag in this function. There's no place where there's a variable in the denominator. There's no place where there's a variable that's inside an even root. Like if I had something like, for example, let's make up a different function. What if I had f of x equals x squared times the square root of x minus 2? We don't have to solve the whole thing, but is there a red flag here in this function?
Yes.
There is, isn't there? Because I've got a square root. And we know that we can't take the square root of a negative number, right? And so if we were to, this is kind of getting ahead of ourselves a little bit, but you guys can handle this. There's the red flag, right? Everything inside that square root function has to be non-negative. Has to be greater than or equal to zero, right? So we could just say, okay, well, whatever's in the red bubble has to be greater than or equal to zero. What is in the red bubble? X minus 2, right? Well, we really want to find the values of x that are going to be allowed, right? So I just need to solve this statement, this inequality for x. What would I do to solve for x? Yeah, just add 2. And so we end up with the answer, x is greater than or equal to 2. That ends up being our domain, doesn't it? You get that? Because those are the values of x that are going to make this bubble non-negative, right? And so ultimately, like looking at graphs of functions is not a great way to find out what the domain is, because, you know, like I showed you, there are situations that look awfully similar, right, but behave completely differently, right? Okay, so given that, let's think about the domains of all these functions. Is there any reason why I could take x to some power? In fact, let's just write it as x to the n, where n is just some integer. There are no red flags there, are there? Right? There's no even roots, right? This is an integer power. This is not a root, is it? Right? This is a different thing. And there's no x on the bottom, right? As long as n is a whole number. We'll say not an integer, a whole number. Can't be negative, right? It's got to be 0 or positive integer. So the domain for all those things is going to be all real numbers. For all the functions that we're looking at. Where did I put that? There it is. So for all these, the domain part's taken care of. That's easy. What about the range? What's the range going to be? What's the range going to be for x to the 4th? It's going to be greater than 0? Or equal to. Yeah, greater than or equal to 0, isn't it? And if I were to do, let's graph x to the 6th. Same thing, right? Or if I graph x squared. Those are all going to be the same, aren't they? Right? Okay. So for all of the even functions, the range is just going to be right? We agree? Oops. It's an odd function. What about the odd functions? Yeah, if we look at the odd functions, like x, or x cubed, right? Those are all functions that are going to plunge down to negative infinity also, right? Okay, so those are going to be all real numbers. What would happen if I were to, let's try something else. What if I were to make the coefficient 6? Does that change anything? Doesn't change anything, does it? Right? It's just going to make it a little bit taller, but it doesn't change the domain or the range. What if I made the coefficient -1? Okay, that does change things. Why does that change things in terms of a transformation? It's been a while since we talked about this, but this is good review. What does it mean if I multiply a function by -1? What does that do? It reflects it over the x-axis. So it should reverse the way the function opens, and so that would change things around, right? Then we go from negative infinity up to 0, including 0. Okay, good. So we can see all that stuff from the graphs. Can we think about it maybe in terms of end behavior? Different approach. This is kind of a calculus issue. This is getting us ready to think about calculus a little bit. So what if we were to take a function like, and let's just go back to plain old x to the 4th for a second. And let's think about this, and when I say end behavior, I mean the limits of the function. We talked a little bit about this before, but let's talk a little more. If we want to say things like, as x approaches infinity, f of x approaches what? Infinity. Yeah. We can see it from the graph. Can we see it from the function? If f of x equals x to the 4th, does it make sense that if x is approaching infinity, now this is, take this with a grain of salt. This is a little trick that we do in calculus. Infinity, you can't really treat infinity like a number because it's not, right? It's boundless. But we get the idea. Infinity is represented by numbers that are positive infinity. Represents numbers that are positively unbounded, so they just get huge without bound, right? So if I were to think about doing something like taking infinity to the 4th, that's a little bit hokey because infinity is not a number, but you kind of see what we're doing. We're saying as numbers get really, really, really big and positive, if I were to take them to the 4th power, what would I expect? Bigger numbers and positive, right? So think about this as f of x approaches positive infinity to the 4th, which really just means positive infinity, right? Does that make sense? Okay, what about the left boundary? So they would call this the right tail of the function, or the right end behavior. Let's try this. As x approaches negative infinity, f of x approaches what? Now think about this. If I took negative infinity to the 4th power, what I'm really thinking about is just huge negative numbers to the 4th power. What's the result going to be? Positive infinity, because regardless of how big a number is, if we take any any negative number to an even power, we should expect a positive outcome, right? Does that make sense? So we're also going to get positive infinity. Well, if you take those two behaviors put together, doesn't that describe the range of this function? Right? Because we know that the lowest it can go is 0. Right? We know it can't be negative because it's to an even power. Right? Does that make sense? Okay. What about if we compare that to what's it do then? How about this? What's it do if I make the coefficient -2? How does that change our thinking on this? If f of x is now -2x to the fourth, you see how that's going to switch things around? Then as x approaches positive infinity, I'm going to have this positive number that we're getting from x to the fourth times a negative coefficient. And what's the sign rule? Negative times positive is negative. And so that's going to make both of those negative, right? Okay, how about this one? Let's try -x to the fifth. Okay, does that make sense? Somebody explain to me, why is it that as x approaches negative infinity, f of x approaches positive infinity? If f of x is -x to the fifth. What do you think?
Because if you take the negative number and it goes to the power of 5, it still stays negative, and then a negative number becomes a negative number.
Good. Okay. Okay. Here's maybe an easier way to condense our thinking on this. That's right. What's the magnitude? Numbers really just have two things. They have a magnitude and a sign, right? You're gonna, how big are they, and are they positive or negative? Well, if I take any kind of infinite number, either positive or negative, to some power, would you agree that's only making it way, way, way bigger? So the infinite part is given, isn't it? We know here that part we know completely. It's got to be infinite. The only question is, what's the sign going to be? So all we really have to do is just play the sign game with the two factors in this problem. We can really just break this into two parts. We've got the -1 times the x to the fifth, right? So what are those signs going to be? Well, if x is negative, x to the fifth is negative, isn't it? Right? So we're going to get a negative times a negative, because -1 is constant and negative, and negative times negative is positive. Okay, get the idea? So then what would, I'm going to throw something a little harder at you. How about, what do you think? So Maisie, what do you think? We know it's going to be infinite, right? Because we're taking an infinite number to a huge power. What's the sign going to be? Negative. Good. Because I'm going to get positive times negative is negative. Good. Okay, how about this one?
Why is it?
Good question.
Because it's an odd number.
Yeah, because this is odd, so a negative number to an odd power is going to be negative, right? Times positive is negative.
Where do we get the negative out of? Because it's odd.
Because it's
So
negative
it's
infinity.
doing
As
the
x
rotation
approaches
and
negative
it's
infinity.
No.
Okay, so and by the way, the way we'd write this in calculus is totally different. This is kind of just like a baby step to calculus. I mean, it's kind of weird that we would write it this way. What we would say is the limit of f of x as x approaches negative infinity equals negative infinity. That's how we'll write it in a couple of years in calculus. Okay. Yeah, how about this one? This is totally different, but I'm just gonna throw this at you and see if you can figure this one out. So what if we have the f of x equals negative 3x to the 6th divided by take a second and try that one. This is way beyond anything I'll ever do. I'll give you a hint about one thing, because you might be wondering. This is kind of weird. You might be wondering, okay, well the bottom's getting infinitely big and the top's getting infinitely big, but as we'll find out in calculus, because the top is getting big faster, the answer is that's bad infinity. The answer is infinity. I'll tell you that much. Okay, but I want you to try to figure out the sign. What do you think? Kirk, what do you think? Positive. How come?
Good morning, Pendleton High School. This morning we will be running a fire drill, but I wanted to announce that instead of going to the zones, just go out of the building if you would, please. You are not required to go to zones today. Again, we will be running a fire drill shortly. You do not have to go to zones today due to snow. Thank you.
Why?
Well, that's kind of a bonus. We don't have to go down to those zones. Okay, so Kirk, you were saying, if we try to evaluate this at some negative huge number, you got positive because how many factors do you see up there? How many different signs did you consider? The negative 3, the x to the 6th probably, right? What's that going to be? Positive. And then this factor on the bottom. And what's that going to be? If x goes to negative infinity, wouldn't x plus 2 also go to negative infinity?
Yeah.
To the 5th would make it negative. And what's our sign rule for that? On the top we get negative, but negative divided by negative is okay. So this is even way above what you're going to do on the assignments, but you get the idea. That's pretty cool if you think about this. One of the big questions.
How'd you get the negative on the
To be continued. Okay, here's the next one I want you to tell me what's going to happen with.
Oh, I did write that down.
Okay, have a look, please. All right, phones away. Everybody here, let's do a quick exercise. Stand up real quick. Everybody stand up. Stretch legs. Put the phones in your pockets, and then sit back down. How's that?
I'm sorry, but I had to sprint 400s yesterday. I'm not doing that. Holy crap!
Okay.
I was like, I'm not sitting up for like that. Yeah, we had to sprint and also like kicking. I had 4.
How about that one?
Wait.
There's a lot going on there, huh?
Okay.
So let's take the top example. As x approaches infinity, there's a lot of stuff going on, right?
Oh.
How about as x approaches negative infinity? Now you've got certain parts of this function that are wanting to get big and positive and certain parts that are wanting to get big and negative. You got these coefficients, so the x to the fourth, I've had this really small coefficient by it. What's going to happen?
Nothing.
Let's see. How about if we just explore this one? Let's take a little tour of this function.
Oh, gosh.
Okay, so there it is, right there.
It's a one.
That's the function. So it looks like, okay, so that kind of, right there, that kind of looks like maybe the winner, the term that won is the x term, because doesn't that look like the line y equals x?
Yeah.
Okay, interesting. There's some real, that's, now notice where we are. We're very close to 0, right? And look at the scale of this thing. We're on a pretty small scale. Okay, let's just zoom out a little bit and see what happens. As I zoom out, yeah, it looks like that's the winner. Y equals x, huh? That's the part, it's the term that, something happened. Something happened. So that, what's that look like to you?
X squared.
X squared. So x squared must be the winner. That's the winner.
Oh, just wait. He's gonna zoom out again and something else is gonna happen.
Let's zoom out a little more. Just see if.
I told you.
Yeah.
Oh.
Hang
You've
on.
been memed.
Hang on. Okay, so what's that look like?
X cubed.
That looks like more like an x cubed function, doesn't it?
Okay. One more time.
Zoom out again.
Are you gonna scroll out and square?
You got me. Okay, so yeah, so x cubed appears the further out we go, we're kind of walking down this function, right, towards the bigger values of x. And if I go all the way out, what do we get? Okay.
I'm so confused.
So you see what happens?
Your eyeshadow looks nice, but your foundation looks horrible.
Oh.
Here we go. Hang on. So there's a really important moral to this story. We saw something. Let's kind of dissect what just happened. So the further out we go, the more the higher powers of x mattered. Why were they so insignificant at the beginning?
Because they're multiplied to such a small number.
Okay, for one thing, because they're multiplied to such, by such tiny coefficients. But there's something else going on. What happens if I take something like 0.1? What's 0.1 squared? 0.01. What's 0.1 cubed? 0.0001, right? 0.001. Sorry. So if you take numbers less than 1 and you take them to increasingly higher powers, they just get small faster and faster, right? So around the origin, when numbers are really small, it turns out that in this polynomial we were looking at, these were the dominant players, right? And as x got slightly bigger, and then those coefficients took over, and because these other terms were being suppressed by these coefficients, gradually the x squared took over from the x as x got bigger, and then the x cubed, even though the coefficient was pretty small, as x got bigger and bigger, the x's overpowered the x squared, right? And then eventually the x to the fourth wins, right? And it has to win, because let's think about this for a second. As x approaches either positive or negative infinity, sure, all of these terms are going to get infinitely big, right? But what does x to the fourth mean when compared to, for example, x cubed? X to the fourth is how much bigger than x cubed? X, right? Because you're multiplying x cubed by x. But as x is approaching infinity, how much bigger does that make it? Infinitely, right? And so it's a growth issue. The leading term here, the x to the fourth term, is growing infinitely faster than x cubed. So even though x cubed is getting infinitely big, because this one is getting infinitely big infinitely faster, this is the only one that matters. That's a really important lesson to learn in math, is that when you want to look at the behavior of a polynomial, and that's what this is, by the way. I need to introduce the word polynomial to you. That's something that you guys have probably heard before, but I want to show you a quick picture. Let's see, where is this thing? Okay, here's kind of the right here. Okay, this is, if you look closely here, this is just in the textbook. This is how we describe a polynomial function of degree n. It's this part. Here, I'll take a picture of it. How about? Okay, that's a polynomial of degree n. I want to get one other thing for you here. Okay. So that's what a polynomial looks like. What's that mean? Polynomial is just a sum of a bunch of terms. Of the functions we've looked at, except for that one where I divided by x, that was not a polynomial. But all the other ones we've looked at today have been polynomials. Poly means many, and nomials just means terms. So each term is represented by a coefficient and a power of x, right? What are the rules for a polynomial? Very simple. The coefficients are just real numbers. They could be anything. It could be pi. It could be the square root of 2. Usually they'll end up being, when we look at like sort of simple examples, they'll be integers, but they don't have to be at all. They could be anything. What about the exponents? What do the exponents have to be?
Positive.
They have to be whole numbers. They could be 0, because what's the power of x associated with that last term? 0. Yeah, it's there. We just don't write it. There's an invisible x to the 0 there, right? So the exponents are whole numbers and the coefficients are real numbers. But what we just decided was, if we want to look at the end behavior of a polynomial, what's the only term we have to focus on? The biggest one. All we have to focus on is what's called the leading term. And it's the leading term because we always write polynomials in a specific order. When they're written in their standard form, we always write them with the biggest power of x first and then descending powers of x all the way down to the weakest term, right? So the leading term tells us the end behavior of a polynomial. You can ignore all the rest. Does that make sense? Okay? All right. Oh. Okay, on your way out, this stuff, by the way, this is called paper. We haven't seen a lot of that in class. I'm going to actually just give you guys a little paper assignment. So grab that off the corner of the desk. On the way out.